And Sung-Sik,
yeah.
Feel free to share screen now.
Okay.
So you control.
Can you see the screen?
Yes, we're good.
Okay, good. Yeah, thank you.
So Sung-Sik, are you ready?
Yes.
Okay, great. Let me introduce you. People will gradually join. Let's see. Welcome, everyone. 너 today 환영합니다. Welcome to Harvard CMSA Kinematic in Math and Physics seminar series. Today is our great honor to have a Professor Sung-Sik Lee from Perimeter Institute and McMaster University. Sung-Sik previously studied at KISTI and also a post-tech Wuhan University. And then he went to MIT and KIT for postdocs. Currently, he's a faculty at the McMaster and the Perimeter Institute. Today, he will be speaking about quantum gravity. So something wrong with my screen. I think quantum gravity from quantum matter. And I would like to remind audience, please feel free to interrupt, ask questions. I think the success of the seminar really relies on the audience. So you shouldn't just, look around and then waiting for me or other people to ask. You should really ask to make it successful. So, okay. So thank you. Thank you very much. Also, show 감사합니다. Thank you. Please take over.
Okay. Thank you, Javan. Okay, thank you for the invitation, and glad that I have the opportunity to share this story. So this talk is based on these two papers posted on the archive, and this talk is about quantum matter and quantum gravity. And as Juben mentioned, feel free to interrupt me anytime during the talk. So in general relativity, we know that geometry is dynamical. Now in quantum gravity, we expect that topology and dimension become dynamical as well. It's because when quantum fluctuations of geometry are very strong, then in priori, there's no reason why topology and dimension remain well-defined. So ultimately, we may want to construct a theory of quantum gravity in which geometry, topology, dimension, and maybe even signature of spacetime are all dynamical. Okay, so where do we start to achieve such goal? Maybe there are many different approaches, but then one approach that we learned most recently from ADS-CFT correspondence is that geometry may be nothing but collective variables of ordinary quantum matter. Okay, and we are taking this approach, and our goal here is to construct a concrete theory of quantum gravity where dimension, topology, and geometry are all collective variables of some underlying quantum matter. Okay, so that is the goal. So here is the plan. So I will first discuss the kinematic structure of the model, and then discuss gauge symmetry and dynamics of the model. Okay. So the fundamental degree of freedom of this model is a real matrix. It's an n by L real matrix, and it's denoted by phi. And here A is a row index that runs from 1 to n. And from now on, I will call this row index as a flavor, okay, for convenience. And then the column index I runs from 1 to L, and I call that site index, okay? So roughly the picture I have in mind is that there are L sites which are going to form some spatial manifold in the limit that L is very large, but not fixing the manifold yet, okay? They are just L sites, and at every site, there are m scalars. Okay, so that's one way to view this matrix. And as usual, the Hilbert space is spanned by this basis state, where this phi is an eigenstate of this matrix operator, and this basis state is labeled by its eigenvalue phi. Okay, and we can say decompose this basis state as a direct product of those basis state at each site for each flavor. Okay, and then we use the standard inner product defined by this. Okay, so this is the kinematic Hilbert space. And to define some notion of extended space or locality, we would like to decompose the total Hilbert space as a direct product of local Hilbert spaces. One way to do that is, say, we define a local Hilbert space at site I from those basis vector, basis state for all flavor, but with that fixed site I, okay? Then obviously the total Hilbert space can be written as direct product of those local Hilbert spaces. But this is not the only way of decomposing the total Hilbert space into local Hilbert spaces, because I can rotate the side indices, say through right multiplication to this matrix. So here, G is a special linear matrix, L by L matrix. And here I have chosen the special linear matrix such that this inner product is preserved under the rotation. And then in this rotated basis, say capital I, now this capital I defines a new notion of site, okay, in this language. And the total Hilbert space, the same total Hilbert space can be decomposed as a direct product of those local Hilbert spaces in this rotated frame, okay? Okay. And in general, this special linear transformation is a group that is much bigger than the permutation, obviously, and therefore, in one frame, say some quantum information is stored at local quantum information stored in one site, in one frame, and then in a rotated frame, in general, that information is spread over multiple sites. In this case, so we call a particular decomposition of the total Hilbert space a choice of frame. Okay. Okay, so I see a raised hand.
Yeah, sounds like will it be more natural for quantum mechanical system to choose the coefficient to be C? For example, the SL was C in the field.
Yeah, maybe you
instead
can
of real.
Yeah, here I have chosen real because my field phi is real. But I think one can consider a complex matrix as well. Here I have chosen this phi to be M by L real matrix. So that's why I.
And there's nothing gain if you choose C, or you will equally good as choosing R.
So sorry.
You don't gain anything if you choose C. Is there something different if you choose C? Maybe more. Anyway, I would just ask.
Yeah, in this case,
doesn't matter.
In this case, we have to choose the real to maintain this rotated matrix to be real. But I think it's not that different. Yeah.
I have a question. Do you want to maintain certain locality? Means the big I and the little I are kind of close. I mean, the only when big I, little I are close together, they have a mix.
No.
Otherwise, you may spread information all over the place. Do you want to
right,
avoid that?
So far, I'm not limiting to. I don't have yet any notion of what is being close and far. Okay. So therefore, this special linear group includes very general transformation that can mix, that can rotate any site into any other site.
Okay. Yeah.
So it's quite non-local so far. So suppose we have chosen a frame, okay? So and then now we can ask if a state of a matrix has any local structure or not. And I say a state has a local structure if the following conditions are satisfied. So the following condition is this. The first is that there exists a mapping from site into a manifold, okay, into a Riemannian manifold with some well-defined topology and metric, okay. And more precisely, I think I want to have a mapping from a site into a region in the manifold, such that the whole manifold is a union of images of those sites. Okay, and then that's the first condition. And then the second condition is that if I choose any subset of site, okay, and then if I look at the entanglement entropy of this subset, then in the limit that the size of the subset is large to the leading order, the entanglement entropy scales with the volume of the boundary of the images of the subset. In other words, when we view that state as defined on the manifold, the state obeys the area, the boundary law. Okay, if that is the case, then I say that state has a local structure. So when I say a certain state has a local structure, that means there exists a manifold with a well-defined topology and geometry, and the entanglement of any subset can be obey the area law or the boundary law of that manifold. Okay, so that is, if that is the case, then I say that state has a local structure. So this is rather abstract. So let me discuss.
Sung-Sik, a quick question.
Yeah.
In quantum mechanics, if you take a typical state, it doesn't have to be satisfy an area law.
Yeah.
You will have usually a volume law.
That's right. So those states that have local structures are a very special set of states. That's right. Yeah. Okay. Hank raised a hand.
Yes. Hello, Sung-Sik. So I have a question. So you're assigning sort of these matrix variables to sites, but and also here the Riemannian manifold you're considering is 2D, right?
It doesn't have to be 2D. It depends on, so some state have a local structure in 2D. Some state have local structure in 3D or 1D. Right.
So like now, what I want to understand is like in higher dimensions, when you need to like assign, for example, like matrix variables on lines as well as sites, like extended defects, so to speak, right? Because at least just from my understanding of homotopy theory, right, you have the uniformization theorem where on 2D you can, you can sort of determine the topology and geometry of 2D Riemannian manifolds using, holonomies between 2 points essentially. But in 3D and higher dimensions, you need like 2 holonomies essentially between lines and stuff. So
yeah. So maybe I will discuss more about how to precisely determine the geometry a little bit later. But here, this is just rough picture. I will explain more how to precisely determine the metric, say. And so for now, let me just give you some example, some picture.
May I ask something?
Yeah.
Is a Riemannian manifold here has the metric of a Einstein type of Euclidean? Is it a plus, minus, minus? Is this signature?
So here I'm thinking of this site forming a space with say Euclidean signature.
Okay, fine.
In this particular example.
No problem. Will you be able to have some emergent Lorentz structure discussed later? I
Yeah.
just curious to ask.
Yeah,
Okay.
that's right. Yeah,
I'll be asked more later. Okay.
yeah, it will come. Yeah.
Thanks.
So here is example. Suppose I consider following state. So this is a state of those matrix labeled by some collective variable t. Here t is L by L complex matrix. So you can view it as some variational parameter or some label for state. So the wave function of state is nothing but this is a Gaussian e to the I times Tij phi I phi j with the flavor index summed over. So it's a wave function is Gaussian. Now this is a L by L complex matrix, and then if this Tij matrix is diagonal, then obviously this is a direct product state in this frame, so there is no interside entanglement. But if this has a non-zero off diagonal elements, then it creates non-trivial entanglement. So for that reason, I call this Tij describe entanglement bonds. Okay, so indeed, if I measure, say, mutual information between side I and j, then in the limit that this off-diagonal element is small compared to the diagonal elements, the mutual information is proportional to square amplitude of Tij to the leading order. So now I can visualize a state in terms of those entanglement bonds. So here, these are the side, and then the line means that there's some non-zero Tij elements, and then thickness of the line represent the amplitude of Tij. And you can imagine what this state represents. And then this is like, maybe we can call it typical state or some genetic state where if you have any side, if any side is entangled with any other side, then, you know, this state has no local structure, okay? It's kind of small world network. But I can consider a very special state like this where I turn on non-zero Tij or entanglement bonds in this particular way, such that this entanglement bonds form a chain, some one-dimensional structure. Then we say this state has a one-dimensional local structure because it's easy to see that, you know, if you choose any subset, then the entanglement entropy of the subset obeys the boundary law with respect to the 1D manifold, okay? And then for the same set of site, I can consider a different state where I turn on some additional entanglement bonds like this. And as you can see, this is some distorted square lattice. And this state has 2D local structure, okay? And as you can see, if you look at, say, this point and this point, for state that has 1D local structure, you can imagine the distance is really far because to communicate, you have to go through this, this long chain. Whereas in the second state, this state and this state is very close. So idea is that we want to define the notion of distance between site from how they are entangled in a given state. Okay, so that's the picture. And one point that I want to highlight is that this local structure is frame dependent. Suppose in one frame, I consider a state with 1D local structure like this. So this is, I turn on entanglement bonds along this chain, and then this state basically describes many copies of decoupled 1D chains. Okay. But if I look at the same state in a rotated frame, where this special linear rotation mix site in different chains. For example, a site, imagine a site in this rotated frame denoted as this square is made of some linear combination of 3 sites in different chain, right? You can consider such transformation. Then in this rotated frame, this entanglement bound matrix Tij now has a non-zero matrix elements between sites that are in different chain. And then therefore, in this frame, this state has 2D local structure. Okay, so and this is due to the fact that this special linear transformation can make a linear superposition that combine multiple sites to define a new sets of sites. So therefore, in a rotated frame, the Hilbert space is sliced or partitioned in a different way. So therefore, entanglement structure changes. So therefore, local structure changes. Okay. Okay, so this is the kinematic structure. I defined the Hilbert space inner product, and I also define local structure that can be defined in once we choose a frame. Okay, so now let's talk about the gauge symmetry.
Excuse me, let me ask you a question here.
Yeah.
If you start with a product state, then looks like the corresponding space will be kind of not so well defined, like a discrete. But starting from product, you can always do some kind of a local unity transformation to mix the neighboring states, and then to produce some kind of a manifold, a notion of a manifold, a local structure. So so the concern is that, for example, for a gapped quantum system, whether one can say that one can always somehow change that into something like a product state because they have sovereign correlation, then the gapped system don't have a well-defined geometrical interpretation. And maybe only for gapless system there's a geometry. The concern is that whether this definition of a local structure by this SLN is looks like it's very general, looks like you can change a lot of states into product states. Then there's no geometrical interpretation.
Yeah, that's right. So I think that's right. The geometry is not invariant under these transformations.
Okay.
So because this transformation is bigger than the usual diffeomorphism. So under the diffeomorphism, the geometry is invariant.
Yeah.
Here is the gauge. So later we will promote this into a gauge group, and this group is bigger. So therefore, geometry cannot be defined unless we can specify a frame from some physical degree, in terms of some physical degrees freedom.
I see. So do I have some kind of intuition that only gapless states have always have a geometrical interpretation? So one require that. Gapless states can always be mapped into product states. Then it's more or less like a discrete geometry, or there's no geometry.
I think here, so one can ask whether these states is a ground state of any gapped Hamiltonian, 1D gapped Hamiltonian. But I think yeah, I think these are states with the local structure are the one with short range entangled when we view those states within this defined within those manifold. And so in the sense that they obey the area law. But here we do not have Hamiltonian or the gap or energy yet.
Yeah, but yeah, the sharply entangled is fine. But my concern is that once you have a one-dimensional sharply entangled state, you can do further transformation to make them unentangled. So then one may conclude one never have a one-dimensional structure because all the one-dimensional structure with the sharply entanglement always became unentangled, then became discrete. Yeah, that's my question.
Yeah, so I think first, not all state can be transformed into a direct product state. I mean, maybe this simple state, this kind of simple example, you can do it, but not all state can be mapped into an entangled state. Okay, and then the second point is that even if certain state can be mapped into an unentangled state, for example, in this example, that is possible, and that's because you have a freedom to redefine the notion of local site. So in a very non-local basis, that state may look like a direct product state. So yeah.
Okay.
But in like the ADS CFT correspondence, it's like the CFT side is always gapless, right? Is that maybe related to this point?
It doesn't have to be gapless. I mean, if the boundary series has a gap, then the dual geometry has a different structure. It doesn't have. It has some finite IR cutoff. But here it is.
So okay, so it would be something like that would represent if you had a short range entangled state here. I assume this is all kind of connected to the holography in the end, right?
Yeah. I think it has some connection, I think. But here, maybe the radial direction that we want to have is like time rather than another space. But it is related.
Yeah, okay, so I have a related question. Implicitly here, you're working in a time slice, aren't you?
Yes, yeah.
Okay, so in a sense, because everything you have discussed is static entanglement, effectively.
Yeah.
So in that sense, time is playing a different role?
Yes, yeah. But we will see how time enters a little bit later. But here, so far, there's no time, there's no space, just Hilbert space and.
Well, but your states, so at some point in time, no pun intended, you will have evolution.
But actually, I mean, in this particular example, this manifold, 1D or 2D manifolds are all Euclidean. But actually, there are states where the signature of this manifold is not Euclidean.
Okay.
Yeah. So.
But how does that affect the entanglement? Because the entanglement, the way you defined it,
so this picture applies only for the Euclidean case, as I.
Okay. Good. Thank you.
But this is only the rough picture. The more precise definition of geometry will come later.
Sung-Sik, just make sure. So for the system of L sites, do you have a finite or infinite dimensional total Hilbert space? Just to make sure.
Finite dimensional Hilbert. Sorry. So the number of sides is finite.
Right, but you have
for phi itself is continuous value.
Right, so that's the thing. I was wondering, maybe that doesn't count total finite total Hilbert space dimension is not finite, right? If you
That's right.
choose, but can you choose a discrete value, maybe just z instead of real number r? Or
Yeah, I don't think any obstruction in doing that. Yeah.
Oh, okay. That may be favorable for some other people who want to put on computer. But thanks. All right, thanks.
Can I ask, sorry.
Yeah, sure.
Just easy question. What is the role of the capital Roman indices? It seems like if you just took real valued phi's, with just the lowercase indices, you're able to encode any graph. So you already have geometry. So what does the capital A index buy you? It just seems to be duplicating the theory, no?
That's right. So far it doesn't play much role, except that it makes this collective variable semi-classical in the limit that the number of flavor is large.
I see.
Yeah.
Okay, thanks.
Yeah. So let's move on to gauge symmetry. So before we do that, let's review the gauge symmetry in general relativity. Okay, so, and I'm using the Hamiltonian formalism here. So it's natural to, natural to discuss the gauge symmetry in the Hamiltonian language. So imagine, imagine we, in GR, if we have a 4-dimensional space and time and space, and then we consider some time slices, and then within each time slice, we can consider spatial diffeomorphism that is generated by this momentum constraint. So here, the generator of spatial diffeomorphism is labeled by this vector field C, which basically label the direction of spatial diffeomorphism as a function of spatial coordinate. And then the Poisson bracket between two spatial diffeomorphism is proportional to another spatial diffeomorphism with a shift. This with a shift given by the Lie derivative of those two shifts. Okay. So this shift is a vector field that specifies the infinitesimal diffeomorphism within a time slice. But in GR, this under this diffeomorphism, the topology and dimension remain the same. But in our theory, we want dimension and topology to be a dynamical object. So therefore, in general, we would like to have a transformation that can map any point into any other point, because these 2 points can be very close to each other in some state. So in those states, the map that transform that side to another side should be regarded as a local diffeomorphism. Of course, in other state, if the distance is very large, then it is not local local transformation anymore. But at least our gauge symmetry should include smooth diffeomorphism in any dimension, any topologies, which is a property of states. So therefore, the spatial diffeomorphism must be big enough to include transformation that rotate any side into any other side. So this is the motivation why we choose this spatial linear group as our gauge symmetry. So we now generalize this this spatial diffeomorphism into generalized spatial diffeomorphism, and then the generator of this transformation is written as this. So here, phi is again the m by L, the matrix operator, and then pi is the conjugate momentum, which can be viewed as a L by M matrix, right? So pi, the conjugate momentum, is this in the phi basis, okay? And then Y here is L by L traceless matrix, okay? So it plays the role of shift vector in general relativity. But it is at this stage, we just view this Y as a label for different rotation, okay? It's labeled for different generators, okay? So this is the generator of SLLR transformation. And we call this Y, the L by L traces matrix, as a shift tensor, a generalization of the shift vector field here. Okay.
So what is M? Can M equal to L, or M is much less than L?
M, we will consider the limit where M is much bigger than L, which is much bigger than 1. Okay.
Okay.
Otherwise, gauge symmetry is too big to have any physical degrees freedom. So, okay. So that's the generalized spatial diffeomorphism. So just to see that this transformation includes at least smooth diffeomorphism, let's consider how this fundamental matrix operator is transformed under SLLR transformation. So under this infinitesimal SLLR transformation, this matrix phi is mapped into phi times some the SLLR matrix. And then in the limit that epsilon is small, we can expand it like this. Okay, so far here is exact. But now suppose we consider a state that has a local structure in a frame. And then suppose this phi, expectation value of phi, varies slowly as a function of spatial coordinate within that manifold. Then we may, so basically this index J plays the role of spatial coordinate. And when this phi field varies slowly in space, we can do derivative expansion like this around J equal I. Okay, so here Rj is the image of side I, right? We have a mapping from each side to a manifold, and Ri is the image of side I in the manifold. And we can now view this as a phi of Rj, right? In the limit that L is very, very large. And then we can do the gradient expansion like this. And then after doing the gradient expansion, we can sum over repeat this side index J here. So from the first term, you obtain this term, okay, where this zeta here is just sum over this shift tensor along the one column, okay, and this first term is nothing but a wide scale transformation of the field of this matrix, and then the second term is the proportional to the first derivative, and then once you contract it, once you sum over J index, it gives rise to a vector field C. So C mu is basically the first moment of this shift tensor. Okay, and then indeed this term is the diffeomorphism, and then this dot 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 is the higher derivative term. Okay, and then the idea is that when this phi is slowly varying in the space, this dot 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 will be smaller compared to the first two leading order terms. And another point is that here we are talking about active transformation for a fixed coordinate system. Okay. So now here is an example. Let's consider the Gaussian state that we discussed before, labeled by this entanglement matrix Tij. And suppose we consider a state with a 1D structure where Tij has some order of 1 diagonal elements and some small off-diagonal elements in this frame. And I for convenience, I label this site using some one-dimensional label, because that's the natural coordinate system. And then in that case, the mapping from site to a one-dimensional manifold is just this. Okay. And then if we consider, say, SLR transformation with a shift tensor that is antisymmetric like this, okay, then under the SLR transformation generated by that shift tensor, the phi is transformed into indeed to the linear order in the derivative expansion as a smooth diffeomorphism. Okay, so how about Hamiltonian? So before we discuss our Hamiltonian, let us go back to GR and review the Hamiltonian constraint in general relativity. Okay, so Hamiltonian in GR is the generator of the gauge symmetry that pushes some time slice into another time slice. So this is again X and T, and then under the Hamiltonian, this Cauchy surface defined in one time slice is pushed forward or backward. Okay, that is generated by Hamiltonian, and then this theta is called Leff's function. So theta is in general function of space here, and this theta of X determines the kind of rate at which this this surface is moving forward, and that can in general be dependent on space. And then the key property is that under the spatial diffeomorphism, the Hamiltonian density transforms as a scalar density, so that fix this Poisson bracket between momentum constraint and Hamiltonian constraint. Okay, but this is just a kinematic structure. There's no dynamical information here. More non-trivial object is the Poisson bracket between two Hamiltonian constraints. So if you evolve your state with one Leff's function first, and then followed by evolution by another Leff's function, and then if you do in the opposite order, then the difference between the final state is related to each other through the spatial diffeomorphism. Okay, so that is encoded in this expression where Poisson bracket between two Hamiltonian constraint is proportional to the spatial diffeomorphism, where the shift that you have to do to match the final state in the second evolution to the final state in the first evolution is obviously dependent on those Lef's function. But importantly, it also depends on this dynamical variable. Here, S is the signature of time relative to space in GR, and G mu nu is the contravariant metric of space manifold. Okay, so in other words, the right-hand side, the Poisson bracket between two Hamiltonian, thus depends on the dynamical variable. Okay, so and this will be important for us, and we will be using this to extract what the metric is going to be in our theory. Okay, so the non-trivial property that we want our Hamiltonian to have is this. In the Poisson bracket is related to the commutator in quantum case. So we want the commutator between two Hamiltonian to be proportional to the generator of the spatial diffeomorphism, which is the SLLR transformation in our case. So this is the key requirement for us. And this is one Hamiltonian. I'm not sure whether this is unique, but this is the one that I could find that exhibit any non-trivial dynamics. Okay, so here pi is again the conjugate momentum of phi, which is a operator valued L by M matrix. So pi times pi transpose is a L by L matrix. And then to make a scalar, we have to multiply with some symmetric L by L matrix and then do the trace. Okay, and then here in the second term, I divided by m squared to make the first and second term to be same order in the large M limit, and this alpha is a parameter of the theory. Okay, and here V is called the Lef's tensor. Okay, and this will be analogous to the Lef's function in GR. Okay, so now to understand the meaning of this Hamiltonian, let's write this Hamiltonian in the component form in the frame in which the Lef's tensor V is diagonal. Okay, so this V here, this is a symmetric matrix. So you can always find the frame in which the Lef's tensor is diagonal. So in that frame, the Hamiltonian takes the following form here, where Si is the diagonal elements of Lef's tensor. And then the first term here is phi square, is basically ultra local kinetic term, pi square. Okay. And then here, this more complicated term, there are different ways to view this term, but one way to view it is to view this as some kind of hopping term. Okay, the phi j phi k is some hopping term, or in the continuum limit is a gradient term for phi. And then first thing that notice is that here index j and k is summed over all sides. So therefore is quite non-local. You can have hopping between any two sites. However, the catch is that the hopping amplitude between site J and K depends on state. The way to see it is to consider, say, a large M limit where flavor number is very large. Then this flavor index AA and DB and CC are all contracted. So in that case, this object, classical, it has a well-defined expectation value. So if we use some Hartree folk-like picture, then this term can be written in this way, where the expectation value of these two bilinear operator determines the hopping amplitude between J and K. Okay, so in the picture is that if I have a site J and K here, between any two sides, between any two pairs of site J and K, you can have hopping. But the amplitude of the hopping is proportional to the product of expectation value of some bilinear operator defined between I and J and then I and K. Okay. And for example, if you compute this expectation value pi I pi j for that Gaussian state we discussed before, it is proportional to Tij. Okay, it's the inverse of inverse. So in other words, if there is a non-trivial correlation or entanglement between site I and J in this frame and I and K, then you can have a non-zero hopping between J and K. Okay, so in other words, the strength of hopping between site J and K depends on state. Depending on which state this Hamiltonian is applied, the amplitude of hopping is determined. So although Hamiltonian itself looks very non-local, if you apply this Hamiltonian to state that has a local structure, right? One of those examples that has either 1D or 2D local structure, then this Hamiltonian to the leading order in the large M limit behaves like a local Hamiltonian, and that you can check more explicitly. Okay, for example, if you start, if you prepare your initial state to have some 1D local structure like the chain structure, right? If you have this kind of chain structure, for example, and then if you apply this, if you time evolve, you just view this Hamiltonian as some time evolution generator, and if you apply this Hamiltonian, then this initial state evolves, but then it does not immediately generate entanglement, say, between this side and faraway side like this. Okay, this Hamiltonian only generate entanglement between the nearby side with respect to this 1D manifold to the leading order in 1 over n. So in that sense, it's kinematically non-local, but it can describe some local dynamics. And the key requirement that we had is this algebraic structure. So one can check the commutator between these generators of the gauge symmetry explicitly, and the commutator between two SLLR generator is just fixed by the structure factor of the group. This is just a constant. And similarly, the commutator between SLLR generator and this Hamiltonian matrix. So this HKL is this matrix. Okay, this is the L by L matrix HKL. And then the commutator between G and H is proportional to H. Again, this structure factor is fully fixed by the fact that this Hamiltonian matrix transforms as a rank 2 symmetric tensor under SLR transformation. So these two relations are purely kinematic, but the commutator between Hamiltonian is more non-trivial, and the exact relation is that the commutator between two Hamiltonians is proportional to the generator of special linear transformation and Hamiltonian itself. But the contribution for the Hamiltonian is sub-leading in the large M limit. So in the large M limit, to the leading order, it is proportional to the generator of the what we call generalized spatial diffeomorphism. And this structure function, as we expect, depends on dynamical variable. It's not just constant. This rank 6 tensor C depends on U and Q, where U and Q are this bilinear or this matrices. Okay, so this is exact algebra, and the key is that the algebra is closed, and when it happens, we say they obey first class algebra at the quantum level. And then the claim here, I'm not deriving, but the claim is that what one can show is that this algebra, the quantum algebra, reduces to an algebra that includes the momentum constraint of GR, and then the Hamiltonian constraint, and obey the same algebra as GR, provided I identify momentum and Hamiltonian in the following way. Okay, so here in the continuum limit, the momentum constraint is basically given by the first derivative of the generator of the SLLR transformation. So this G, Colli G is same as this G. I just wrote this in the semi-classical limit. And as we discussed before, the shift vector in GR is identified as the first moment of the shift tensor here. And then in a frame, the Hamiltonian density of GR is given by the diagonal elements of the Hamiltonian matrix. And as expected, the left function of GR is the diagonal elements of the left tensor in this theory. Okay, and then finally, most importantly, in order for this to reproduce this part of the algebra in GR, we have to identify a particular combination of this structure function that appears in this commutator here as a spatial metric times the signature of time. Okay, so here this C is a rank 6 tensor that is here, right? Which is given by some this matrix pi and phi. And then this is basically second moments, a particular second moment of that rank 6 tensor. And then if we identify this second moment as the metric times the signature, then this algebra reduces to the algebra in GR.
Sorry, Sung-Sik, can I ask the question?
Yeah, sure.
So this D tensor, D over M, that's a deformation, basically, right, of the classical Poisson algebra.
So which tensor?
D, the D,
D,
big
D.
D, capital D, yeah. So
This one.
yeah,
Yeah.
that one. So like just to, because in principle, I guess you can insert higher order terms in the Hamiltonian that you have written down in the previous slide. So then if I insert, like, for example,
modify the Hamiltonian?
Yeah, here, like if I add more like 8th order term or something like that.
Okay, so in general, if you modify the Hamiltonian, in general, they won't satisfy a closed algebra.
Oh, okay.
The commutator between H doesn't have to be proportional to G and H in general.
Oh yeah, right. It'll be like some power of H, essentially.
So not just power of H, some other operator besides G and H. So if
Right.
that happens, then this set of gauge transformations are not closed. The algebra is not closed. So you have to enlarge the gauge group even further.
I see. So like to get this D, essentially, like that constraints what you have already written down, right? So that's the sixth order term that gets you this D term in the commutator.
Yeah. So the key requirement is that if I have a set of generator for gauge transformation, CA, A is the label for different generator, and then key requirement is that commutator between the generator is proportional to those generator themselves with some structure function that can depend on dynamical value. But we want that to be proportional to the generator of gauge symmetry.
Right.
But
yeah.
In general, if you choose some arbitrary Hamiltonian, then there can be some term, say E, A, B, that is not proportional to the generators of the gauge symmetry themselves. And this is what we want to avoid.
Right. But then if I, for example, like, because I'm just working with phi and pi, right, the conjugate variable, I'm saying, like, can I add higher order terms in those variables themselves in the Hamiltonian that you've written down, right?
Yeah, that's what I'm saying. It's not easy to do that without modifying this.
Right. But then, okay, well, the central question I guess I have is that this D term comes from having the relatively local terms.
Yeah, D term is
okay.
combination of pi and phi as well. Yes.
Okay.
Yeah.
I see. Okay. Yeah, that's the gist of my question. Thank you.
Yeah. So D term is some additional term. It's a quantum effect that is not present in GR. Okay, so
excuse me, maybe can I ask something? So I just want to make sure I still follow the logic. At some point, maybe 1 or 2 slides earlier about the Hamiltonian, you mentioned this relativity local hopping term. I just want to recall, how is the relativity coming here? Do you mean there's already a Lorentz?
No. This relative.
Relatively local. Okay. Okay.
This means that
no problem. It's not as local as ultra local, but it's
I mean,
okay,
there's
it's kind of local. Okay.
Yeah. What I meant was that there's no absolute locality. In other words, in usual local Hamiltonian, we turn on hopping between some specific set of sites, and that predetermines the distance and determines the topology and dimension, etc. Right? But here, none of them is predetermined. Notion of distance between two sides is determined by state. Okay, so therefore this Hamiltonian appears to be non-local, but it has some sense of locality, and that sense of locality is determined relative to the state.
And just make sure also I follow the beginning of logic. So you have the kinematic analysis for the theory, and you discuss the Hilbert space. But what they trigger the dynamics?
Yeah. Okay.
Yeah. Do you just introduce a Schrodinger equation?
Okay. That's the next. Yeah. That's the next topic. Yeah. Okay. I will move on to dynamics.
Yeah. Here I have a question. I'm sorry. So this is G nu nu. Is that depend on the wave function you choose? This meant about the wave function, or it does not depend on wave function.
Sorry. So which one? G.
The G mu nu.
Yeah.
Usually it looks like from the beginning you say the different wave function have different geometry, maybe different G mu nu.
This is an operator. So it's this.
I see. This is all operator. So it don't have a value yet. Okay.
So even the signature is operator here.
Okay, I see.
So now once you have a state, you can compute the expectation value.
Then determine that.
Yeah, that determines G mu nu and S.
Okay. Yeah, thank you.
Okay. So any other question before we move on to dynamics? Okay.
Let me make sure. So I think so far at this moment you are exploring the Hilbert space structure of some real scalar field with multiple finite number sites, and then try to explore the transformation between them, some generalized diffeomorphism, and then you don't really require time at this moment. It's maybe this Ecuador says it's a time slice.
Yeah.
And then you just derive the transformation, and there's a conjugate momentum respect to that transformation, and somehow you can write down Hamiltonian without explore anything about time, but time will come in next. Okay.
Yeah.
Fine.
So in GR, there's no time either. So H is here just Hamiltonian. In GR is the generator of gauge transformation. Same is true here. But you know, what we call time can be understood in the following way. So usually, if we have a gauge symmetry, then what physical state, the gauge invariant state, must be singlets. So they need to be annihilated by the gauge transformation for any choices of the shift and lapse here, right?
Sorry, shouldn't the Hamiltonian commute with these generators also? In gauge theory, they usually do.
Yeah, so where in the gauge theory, we have a generator of gauge symmetry, and then there's a Hamiltonian. And their Hamiltonian is not generator of gauge symmetry, right?
No.
And their Hamiltonian commute with the gauge symmetry, as you said. But here, in theory of gravity, there's no separate Hamiltonian. There are only gauge generators.
Okay.
What we call Hamiltonian in GR is another generator of gauge symmetry.
Okay.
Right?
But in what sense is there a local gauge invariance, if you wish to use that terminology?
So when we say the GR is gauge invariant, what we really mean is that the set of gauge generators form a closed algebra.
Okay.
Okay. So here that remains to be true.
Okay.
Okay. So in GR and here in this theory as well, there's no time. Okay. We only have Hilbert space, and we have a gauge constraint. That's all we have so far. Okay. And now our goal is to understand dynamics from this. So, so usually we want to consider gauge invariant state, but in this theory, one can show that all gauge invariant states have infinite norm, and this we can say because we have a well-defined norm in terms of the norm for the matter field. And this is due to the fact that gauge group is non-compact, and the wave function of gauge invariant states are extended in the space of phi. Okay, that's an intuitive way of understanding. Okay, and physically, this is because a gauge invariant state is supposed to capture not just the state defined at a moment of time, but the whole space-time history. Okay, so therefore, what we perceive as a state at a given moment is only some slice of gauge invariant state. Okay, and usually the way to extract dynamical information in this setting is to look for correlation among what people call partial observable or kinematic variables along the gauge orbit. So here's concretely what we can do. Suppose we consider some seed state, or we may call initial state, but not initial in the sense of time, but some state, which is not gauge invariant. Suppose we consider some normalized state, but not gauge invariant. And then we can project this state to the gauge invariant physical space by applying some projection operator, and then you can view this projection operator as some kind of evolution that generates evolution along the gauge orbit, right? So here H and G are generators of the gauge transformation. Here tau prime is some parameter that labels the gauge orbit, right? And then we can generate a series of states along the gauge orbit, right? And then now we can look for correlation that exists among dynamical variables along the gauge orbit. So when for example, when one observable takes one value, what's the other observable? What's the value of the other observable, and vice versa? So then we can use a subset of kinematic variables as a clock to measure the correlation of or evolution of other variables with respect to the clock variable. So that's usually how one can study the dynamics. Okay. Oh, Juven, you have a question?
Yes, if it's okay. So I suppose you have many. Just make sure, because maybe you will get to the Lorentz group symmetry at some point, but since we also discussed dynamics now, maybe I can ask. I suppose when you have a large N or large L site, as you label GL, L, R, I certainly, these are non-compact, I certainly can find some subgroup which has the global structure of some maybe Lorentz group, let's say SO spin or pin of 1,3. And however, I want to see, is there some way you can find this group, maybe how do they act maybe globally, or how do they come about out of the, maybe it's from GL NR or GL LR in your label, sorry, SLNR, sorry, SLLR, or how does it show up? If you want to have the general relativity, I guess we still need to see this structure. Maybe you mentioned, but I didn't understand that part.
Maybe I didn't fully understand the question, but it's your question that there's some gauge group generated by G and H. It's a big gauge group.
Yeah, that's very big, too big.
And then for a given state, some subgroup of some gauge group, gauge symmetry will be broken, right? For example, the Minkowski space time breaks the diffeomorphism, and then only remaining subgroup is the Poincare group, something like that. Is that your question? How do we
yes.
how do we identify unbroken subgroup of this? Yeah, okay. That depends on state. Okay, so we will discuss that a little bit later. Yeah. So though, yeah. So yeah, we can do that. Yes. And by the way, regarding the Lorentzian spacetime, here, as I mentioned, the expectation value of this operator encodes the information of signature of what we may call time relative to the metric of signature of space. Okay.
But the trouble for me is that it's kind of to me, it's kind of buried inside the indices, and it's very hard for me to see through. So out of the GLNR, is there some metric that globally I can find this O3,1 or whatever, or pin 3,1 structure? These are bosonic. I suppose it's O3,1. Is there some sharp statement? Maybe this is well known, but I'm just ignorant, not knowing how this come about. Is there some sharp sentence or sharp statement? How can we find this global Lorentz invariant or Lorentz group symmetry out of the large gauge group that you introduced?
Yeah.
And also the other thing is that maybe it's obvious, but how about the coordinate transformations? Like, how is that concept building inside the quantum matter? Because I don't think you are using the coordinates for the original. So there's actually no coordinates. You just label the size, right? But how the coordinates, for example, the covariance structure, sure.
The coordinate structure is comes in when you define the map from the side to a manifold. Okay, that's your coordinate system, and you have freedom to choose a different coordinate system. Okay, and here there's a freedom in choosing different coordinate, and there's also a sense in which the theory takes the same form in different coordinate system. But here I'm discussing all this constraint algebra as an active transformation for a fixed coordinate system. But you can phrase it in a different language as well.
Okay. Yeah, I will hear more. Yeah.
Yeah, I will discuss about the Lorentzian signature in a more intuitive way a little bit later. Yeah. So so what we want to do is to generate a series of states along the gauge orbit, and then look for correlation between different variables that exist along the gauge orbit. Okay, and maybe we can choose a subset of the dynamical variable as clock, and then describe the evolution of other dynamical variables with respect to the clock variable. So that's the rough idea. And in doing so, we start from some seed state, okay, and then apply some Hamiltonian evolution to generate those states, okay. And when we do that, it's useful to constrain the subspace that the gauge orbit explore by imposing the symmetry of this sub-Hilbert space. So there's a gauge symmetry, the special linear transformation that acts as a right multiplication to the matrix. That's the gauge symmetry. But also there is a left multiplication. So there's phi. This is a flavor index, and this is side index, right? So the right multiplication here was the gauge symmetry, but then there is some left multiplication which rotate the flavor, and there's a global OM flavor symmetry in this theory, because all the gauge generators are OM singlet. But now we can, of course, state can break some of those flavor symmetry, and here's one example. This is not the only example, but for convenience, I have chosen the following unbroken flavor symmetry, where this is the first L component of the flavor and permutation among them. That's the first part. And then this is the orthogonal rotation in the, okay, maybe here. This is the first L component of flavor. And then there's the next n-L/2 component of the flavor, and we can rotate among themselves using orthogonal group, and then another orthogonal group, which is a subgroup of the global flavor symmetry. This is just an example. Okay, we can consider other symmetry, and then once we choose global symmetry, then we can find the basis that span those subhilbert space. Okay, and for example, in this choice of symmetry, here these are the basis state. Here S, T1 and T2 here are all L by L matrices, and then they are some collective variables of the underlying matrix field. For example, this S is something that is conjugate to the first L by L block of the matrix phi. Okay, so you can view this S as a conjugate momentum of first L by L block of the phi matrix. And then T1 here is something that is conjugate to the bilinear of phi, where phi is this block of the matrix. And then this Colli phi is the last block, and then T2 is the conjugate momentum of those operator. Okay. And then general state within this subhilbert space can be written as a linear superposition of those basis state. Okay, and then this chi is some wave function defined in the space of collective variable. Okay, and then here the nice thing about choosing this basis is that in the large M limit, these collective variables become semi-classical. So we can study semi-classical dynamics in the large M limit. So what we can do is we can choose some semi-classical state as a seed state or initial state, whose wave function is well localized in the space of this collective variable with well-defined momentum. Okay, and then one can evolve this seed state with a Hamiltonian using and generate the gauge orbit. Okay, so here is one example. We have chosen a initial state which have a three-dimensional local structure in a frame in which one of those collective variable Q, remember Q was the first L by L block of phi matrix, where this Q is diagonal. So in other words, here we are choosing the site in terms of flavor. So here we choose the particular frame where it's kind of unitary gauge, right? In gauge theory, there's some matter field, and you can always choose the gauge in which the matter field has some fixed phase. Likewise here, I can always rotate the frame where what I call matter field Q has this particular form. Okay, so this is one way to define the notion of site or frame using some dynamical variable internally. Okay, so I consider a state which has a 3D local structure in this frame. Okay, and then we can evolve this state using the Hamiltonian constraint, and then And then you can look for correlation between geometry and other observable. And here's one result. So here, because this state has the discrete rotational symmetry and translational symmetry, the spatial metric is proportional to delta function, and only non-trivial object here is the scale factor of the spatial manifold. Okay, and here is the scale factor A plotted against the gauge parameter tau. Okay, and here is the signature of time plotted against the same gauge parameter. So it's rather busy, but let's just focus on this window here. So within this window, the signature is -1. So this is a Lorentzian space and time, and it starts here with a very big universe, and then as parameter time runs, the size of the universe shrink and reaches some minimum, and then bounce back to infinity. Okay, so this is kind of one epoch of distal-like space-time with a Lorentzian signature. And then there are some dynamical phase transitions. So if you look at, say, around this point, the signature of space-time jump from -1 to 1. So this is Lorentzian, and then in this window is a Euclidean. Okay. So basically, the picture here, I have a series of Lorentzian space-time manifold, which are bridged by Euclidean four-dimensional Euclidean space. And here's what happens at the critical point. Okay, so here I'm plotting one of the collective variable in momentum space. So here I have a translational invariance. So this Tij, one of the collective variable, depends only on Ri minus Rj. So Ri is the image of each side in the three-dimensional spatial manifold. And we can look at this T as a function of this momentum. And then this is the plot of that T along one choice of the momentum direction. Okay, and here I'm plotting the profile of this entanglement bond spectrum as a function of, say, parameter time as I go through this transition. So what happens, say, is that as parameter time increases, this entanglement spectrum become flatter and flatter. Okay, so that means in real space, this Tij, the collective variable, become more diagonal. The off-diagonal elements become smaller. That's what happens when this become flat in momentum space, right? And then at some critical point here, the two derivative vanishes here. Okay, that I think that is this line, and that's when the size of the universe diverges. Okay, so the picture is that the metric is roughly second moment of this entanglement bond, and at some critical time, if the second moment vanishes, then that's the moment where the sides are least entangled among each other, and in that case, the distance within the spatial manifold become very large. So that is what happens at this moment. And then if you go to this Euclidean case, then there's the curvature become opposite, right? So here curvature was positive, and then here is a negative. So the sign of this entanglement bond spectrum determines the signature of space-time in this case. Okay. So Juven, question?
Yes. Let me make sure this simulations you show in this and the previous slide. What triggered the dynamics of the tau direction in the horizontal? What triggered that this evolution? What's
so this is tau is the parameter along the gauge orbit. So if I have some Hamiltonian, this is the generator of gauge transformation. Then I start from some initial state that has the three-dimensional local structure, and I evolve that initial state using the I'm applying gauge transformation, and then tau is the parameter along the gauge orbit. Okay, so here I'm plotting the scale factor,
yes,
with respect to the parameter time. But there are other dynamical variables, for example, other expectation value as a function of tau. So tau has no physical meaning itself. It's just a gauge parameter. But
okay,
I can use some other factor, other dynamical variable as clock. I don't know whether there's a way to define clock globally. Probably not, but at least within a window, I can use a subset of dynamical variable as my clock to see how, say, size of universe evolve as a function of those clock variables. But here tau is
it's a parameterized gauge orbit.
Yeah, that's right. Yeah.
But you only need to input some any condition at some tau, and then it will evolve. This is a first derivative, first order differential equation.
Yeah. So here, this is just you can view this as just the usual
evolution out of tau.
Evolution. Yeah.
Fine. And how would you like to interpret this result? I see that you have the symmetry sign of the time change from Euclidean to Lorentzian. You have a scale factor A that also blow up.
Yeah.
And it blow up, especially when you go to maybe Euclidean signature. Well, it stays kind of a bound, flat, with most localized smaller value of A at the Lorentzian signature. So how would you interpret this result physically?
So this means that in a gauge invariant state, or one gauge invariant state, or this gauge orbit already includes many histories of space-time, and some part of the histories has a Lorentzian signature, but some part has no time at all, just a four-dimensional space. Yeah, I don't know how to interpret it. Or I can say, if we look at, say, this part of the gauge orbit, okay, it appears to describe our universe, where size of universe shrink and then expand, and then say as a function of this tau variable, some other observer will say expectation value of Q, trace of Q, for example, have some evolution. And then I may choose to use this as my clock within one segment of the gauge orbit. I can ask, what's the correlation between this observer and size of universe? That will be the prediction. So prediction will be, when I measure this value for Q, what is the size of universe? Like that.
Okay, thanks. How do you do simulation to find out this metric Tribunal? How do you compute it numerically?
So here in principle, you have to do the full quantum dynamics, right? Because this is some initial state, and gauge transformation can be viewed as a quantum evolution. Okay, so this is the full quantum evolution. But as I mentioned, in the large M limit, if you start with a semi-classical state like this, which has well-defined coordinate and momentum for the collective variable, that can be approximated by classical equation motion. Okay, so it's like GR. We don't have the quantum theory of gravity yet, but presumably, if you have a full quantum theory, that we could do the similar thing. But in GR, you can do the classical gravity, right? You start with some initial state defined on the Cauchy surface, and then you classically evolve that Cauchy data to future for different time slices, and then you look at the correlation between different variables at different Cauchy surface. Okay, so that will be the prediction of GR. Likewise, we are doing the similar thing. In practice, I'm solving this in the semi-classical limit, in the large M limit. Okay, that's what is being plotted here.
So just to clarify, like you're not doing any Monte Carlo stuff.
No. This is the classical solving classical equation motion.
I see.
In the large M limit.
Right. So essentially, you're just because I'm wondering about like what's the effect of the deformation parameter D, that D tensor. So because I know that you have an equation that relates the product of the signature and the metric to the C, right?
Yeah. So
yeah.
D does not enter in the large M limit because that's the subleading term.
Right.
But in the full quantum problem, there will be a correction due to the presence of D. So yeah, but that doesn't show up in this semi-classical limit.
Right, because you're taking like the continuum, well, close to continuum essentially.
Semi-classical limit. Yeah. Large M limit.
So sorry, what's the difference between this? What's the difference between this semi-classical limit and just classical GR?
Oh, sorry, classical. Maybe just classical. I mean, if you begin to consider small fluctuation around the saddle point solution, then we may say first order quantum fluctuation. But this is classical. Let me just say classical.
So why are you allowed to go through this transition though? Because isn't the classical geometry becoming singular at that point?
Yeah. So at this point, somehow the site lose the entanglement, so that. But interestingly, even at this transition point, at this critical time, say tau c, the entanglement bond spectrum here doesn't become completely flat. It's just that only the second moment, just the second derivative of this thing. Only this thing vanishes, but it doesn't become completely flat. So that means there's still some entanglement. So Tij is not completely diagonal. It's not momentum independent. So there's some entanglement, but that part of entanglement is not captured through geometry. So geometry here, metric is a very specific combination of this collective variable. It's the second moment of this collective variable C, and at the critical point, that become 0. Okay, so that means basically it loses some second moment of the entanglement spectrum.
But shouldn't the classical equations shouldn't they break down at this transition? So how are you managing numerically to go through the transition?
Oh, so the classicality and what breaks down is the continuum of description, but still classical description holds.
I see. Thanks.
I think I still don't get how do we extract the metric out of the theory.
Okay.
Tribunal.
So the metric.
Maybe, formally, I think this formula
is defined by this guy, right? So C is the rank 6 tensor is this object here, which is some combination of pi and phi, right? And then you compute, or you contract this tensor index in a particular way, and you basically compute some second moment of this rank 6 tensor in some particular direction in this space. Okay, that is the metric. And in general, this is an operator. what I'm computing is compute the expectation value of this operator. Okay, for those semi-classical state. Okay, for example, for this initial state. So here I consider some initial state with some Tij, which is non-zero among those nearest neighbor site in the three-dimensional manifold, right? So my state has some structure like wave function is e to the I Tij phi I phi j, something like this with some other term, right? This is the state, right? And then I can compute the expectation value of that metric operator times the signature, which is basically some C, right? I can compute the expectation value of this. That will give the spatial metric at this, for this state. For this state, you can view it as a one-time slice in GR. That gives a spatial manifold. And then now, we evolve this state using Hamiltonian constraint, tau, right? So that will give some state as a function of tau. Let's denote this way, right? And then I can compute the expectation value of metric and time signature, this operator, for this state at later gauge time, gauge parameter tau, right? So that will give tau dependent metric. Okay.
And how maybe I ask this again, but let me just make sure. So how do we interpret the signature change in the sense kind of like the distance measure in that space, the effective space time you define, that you extract the metric G mu. You know, the way we kind of measure the distance rely on the metric. But so when you change the gauge, when you evolve the gauge parameter, somehow this evolves. What this process really mean? I think maybe there's no simple answer, but how's the measurement of the space-time distance somehow change from maybe, let's say, dx squared plus dt squared change to maybe dx squared minus dt squared for the measurement, right?
So that information is encoded in this algebra here. Okay, so the signature of time here, S, is encoded in this algebra, and then in our picture, because here we are using the Hamiltonian framework, so we are treating time and space in a separate way. Okay, but we don't have to commit what the signature of time is yet. Okay, and then the signature of time appears how different kind of left evolution is glued with each other into this closed algebra. Okay.
Yeah. Okay.
And
thanks.
And,
okay. No problem. Thanks.
Yeah, but I think physically, if you view this gauge transformation as usual time evolution, what happens here is some spontaneous flattening of the band. Okay, and then here some entanglement bands become flattened at some critical time, and then it's maximally flat locally at k equals 0, and that's when the size of spatial manifold blows up, because that's where the sites are least entangled. But the interesting thing is that, as I mentioned, even at that critical point, entanglement is not, there's still non-trivial entanglement, okay? Because Tij is not completely diagonal. Only the second moment vanishes. So this means that geometry alone does not fully, maybe this is a trivial statement, does not fully specify the full entanglement pattern. Okay, so very specific combination of entanglement is captured via geometry, and there exists non-geometric entanglement. Now, that is not captured by the metric. Okay, so for example, at this moment, the metric is there's no continuum description. There's no continuous space. Okay, and there's no geometry, but there is still the sides are still entangled in a non-trivial way. Okay. So we may say EPR is strictly bigger than ER, at least in this theory.
Sounds like, can I ask a question?
Yeah, sure.
So here the tuning parameter of this universe is just the initial seed state chi and the gauge parameter tau. Is there any other tuning parameter?
So tuning parameter, there's a parameter in the theory. There's only one parameter, which is alpha here. Okay, that's the only parameter of the theory. And then there are a lot of parameters in the state. Okay, so now when we talk about the space of states, maybe gauge invariant states, there are a lot of parameters. You know, that depends on how you choose your seed state here, initial state, and that number of those parameters depends on the symmetry, the global symmetry you choose. Within this symmetry choice, these are the parameters. So this collective variable S, T1 and T2 are the parameters of the state. Mm-hmm. If you choose different global symmetry, you have a different number of parameters.
And then there's tau.
Tau is a gauge parameter, so that doesn't label different physical state. The tau is like.
It seems you want to interpret the universe living at specific tau.
No. So the tau is like choosing a tau is like choosing a moment of time, but not because tau is a time, but because for a fixed tau, you can define some well-defined expectation value of some your observable that you use as a clock.
Okay, so I should really view a tau not as a tuning parameter of this universe. Instead, I shouldn't even talk about the universe. I should talk about the history of the universe.
That's right.
Which is purely determined by the initial state, initial seed state.
Yeah. Right.
And the parameter alpha, maybe.
Yeah.
So I want to just confirm in the slide previous to this one. So this both chi and chi of tau are not gauge invariant, are they?
They are not. That's right.
And you don't want them to.
So what is gauge invariant? Is the
tau equal to infinity.
If you sum over all tau,
mm-hmm.
with sum over all lefts and shift with different, then that is gauge invariant. So basically, gauge invariant state is extended. Okay, so gauge invariant state pictorially, let me choose to say this way. Gauge invariant state, if I look at the wave function, might be extended like this. Okay, and then norm is infinite. But then we may say, if I specify a value of t, for example, then if I use this as a time, then along this slice, right, you have some state localized at one region in the phase space, and we may identify that as a state associated with a moment of time. I mean, roughly, but this is not a precise statement. It's just I think there is still a conceptual issue how to extract time from this constrained system. I think this is an open problem.
Mm-hmm. And initially, you at the beginning of the talk, you mentioned there could be SL L, R symmetry, and then it's broken by the choice of the initial seed state.
Yeah.
Okay. Mm-hmm. So finally, your theory of quantum gravity does have some global symmetry.
The flavor, yeah, global flavor symmetry.
I don't know this very well, but I have heard that the quantum gravity theory is not supposed to have global symmetry.
I don't know how to. Yeah, I don't know. This has a global symmetry. The state may not have the full global symmetry, but the constraint algebra does have the OM global OM symmetry.
Mm-hmm. Thanks.
I think this statement would be that if you have some, the low energy effective theory should not have any global symmetry, but that's maybe a different statement from saying that the actual description of quantum gravity has some global symmetry as part of the description.
Because the symmetry of the low energy effective theory depends on vacuum, your state around which you expand. So yeah, so maybe that brings to the next final point. So once you find the saddle point, like the distal space, then now you can consider small fluctuations of those collective variables, and you can write down the low energy theory for those small fluctuations. You can write down the Gaussian theory and then interactions, etc. In this particular case, those excitations are described by some bilocal object. So remember T, for example, is entanglement bond matrix. It's a collective variable that are classical in the large M limit. And then in the previous slide, we find some saddle point configuration, and then we can consider a small fluctuation around it. And then this small fluctuation will be the propagating mode that propagate in the space that is set by the expectation value of Tij self. Okay. And then one important point is here is that this bilocal object obeys the local rule. The propagation of this bilocal object, is described by local theory. In other words, you can do the gradient experiment how the endpoints of these bilocal objects propagate. Okay, sorry for going over time.
Sorry, just make sure. Can you divide by local for mathematician? Just support by local here.
Sorry?
Can you divide by local for mathematician?
Oh, bilocal, I mean, it has it depends on two coordinates instead of say one coordinate, right? So you have some field that depends on R1 and R2. Okay, so your excitation has is locate. Yeah, so this is in a sense is an extended object, right? But it's not like string. String is you have to specify whole trajectory, but here you just specify two endpoints. So the excitation is in the space of these two coordinates. Yeah. So for example, suppose again going back to this example, Tij is the collective variable like that describe like this, and then suppose you have some saddle point for Tij, and then you can consider some small fluctuation of this Tij, right? So this is the dynamical variable that the propagating degrees freedom in this theory. Of course, at the fundamental level, the phi, the original matrix is they describe the excitation, right? But we can view this delta Tij as some collective mode of the underlying matrix phi.
And this bilocal field cannot be written somehow decomposed as a tensor product of the fields of two fields.
No.
Phi1 on R1 and Phi2 on R2.
No. So phi R1, R2 are independent objects. for different phi R1 and R3, for example.
But why do you need this by local fields? It comes maybe out of nowhere just until these slides.
So by local because the collective variable that describes different state within this manifolds are this matrix T1, for example, which is L by L matrix T1. So L by L matrix here. T1, the wave function is given by this e to the I times T1 ij phi I phi j. So this is the collective variable. Okay. So it's like in condensed matter system, this can be viewed as some variational parameter. We can consider state with that as a function of some variational parameter, and then you can promote those variational parameter as dynamical variable, right? But in this case, we can show that these variational parameters completely span the full Hilbert space with this symmetry. Okay, so therefore the dynamics within this sub-Hilbert space can be described just in terms of this collective variable, and it's bilocal because it's a link variable where this variable itself defines the link between two sides I and ij, and yeah.
Thanks.
Can I ask a question about just because you said in the beginning of your talk that dimension will also be dynamical, but in this example, it's not, right?
In this example, it's not. Maybe, but if for the same set of site, I could have chosen different initial state with a different dimension, where I could say, yeah, that's right. Yeah, I could turn off all these bands, for example, between the rightmost slice with the rest, and then this slice will describe two-dimensional space, which is decoupled from this three-dimensional space.
Mm-hmm.
And one could, in principle, study the evolution of state where this bond is initially weaker than the rest of the bond, and how maybe somehow space may get fragmented into different part of space with a different dimension. So if we study those evolution, one may see real dynamical nature of the dimension as well.
Right. So in at least like intuitively or naively, this L or the how much you truncate the full Hilbert space determines the space-time manifold effectively, essentially.
Mm-hmm.
But then it seems that the procedure is to first pick that truncation of the Hilbert space and then use that state, use a state in that subspace to compute the expectation values.
Mm-hmm. Yeah.
But then I thought that if you want to determine dimension dynamically, then you should I don't know, it seems that L should be able to change throughout the dynamics, as tau evolves, I mean, for instance.
Yeah, so in this particular example that I studied explicitly, if I choose some initial state with the fixed dimension, then throughout the evolution, at least classical evolution, the dimension is maintained. I think it's an interesting question. If one can choose some different initial state, maybe you have to first break the translational symmetry in some way, and to see some processes in which dimension can change.
Mm-hmm.
And maybe if there's some attractor mechanism where manifold with a certain dimension are more special than the other, that will be interesting.
Yeah.
Then the related question is, how do you know how many components of G mu nu you need? Like here is like 3+1, right? But how do you know it's 3+1?
You don't know in priori until you specify your state. Yeah. So in that sense, dimension is not predetermined here. It is a property of your state. So the full Hilbert space, there will be some state which has a 2D local structure, some state has a 3D local structure, etc. Right? So depending on which corner in the Hilbert space you are in, your continuum description will be completely different.
Thank you.
So here I have chosen the initial state where, 3-dimensional structure is obvious, so that I can choose the coordinate system in a natural way using this 3-dimensional manifold structure. Yeah, but yeah, that's an interesting question. If someone hands you over some arbitrary state, is there a systematic way of identifying dimension or topology? Is there dimension operator you can compute the expectation value that tells what the dimension is? Yeah, I don't know. That's an interesting.
And also the initial state, basic state you choose can also possibly mix between different dimensions.
Yeah, you could consider some initial state which is a linear superposition of some kind of Schrödinger state of with a different dimension. That is in principle possible. Yeah. Okay, so here's I talked about a toy model of quantum gravity, which has a property where dimension, topology, geometry, and signatures are collective variables of some underlying quantum matter. And this theory has some property that is closely related to the general relativity. And one can take the classical limit and study the classical dynamics in this theory. Okay, I will stop here. Thank you for your questions and attention.
Thank you very much. All questions from the audience.
Can I ask again about the connection with ADS CFT? If you should be able to describe in this some spacetime that's asymptotically ADS, and then does it somehow look like a CFT, but in one less dimension? How does that work?
So in this case, the picture is that I have some kind of d-dimensional, where this is not fixed, but the manifold that these sites are embedded into. If the state has some local structure, I suppose this has some 2D local structure, then this has a d-dimensional local structure, and then the gauge transformation generated by this Hamiltonian is the emergent direction in this case. Okay, so in contrast to the usual ADS-CFT, in the usual ADS-CFT, you have say time and then space direction. So you have a unitary theory defined on the boundary, and then there's some RG transformation. Some operator can think of that acts on some. You can define some. Yeah. Okay. So maybe I will spell out that more. So this radial direction in ADS-CFT can be viewed as RG direction, and then RG transformation can be viewed as transformation generated by some evolution operator acting on some state associated with at this boundary. Of course, here the boundary is a space-time, right? So it's not the usual state, but we can formally define a state defined on the space-time. Okay, roughly speaking, e to the is. This is the action of the field theory. We can view this as some wave function of the state. And then RG transformation can be generated by applying some coarse graining Hamiltonian acting on this state, okay? And there's a way to understand how the coupling function or coupling constant can be promoted into dynamical variable in the bulk, and how that can include the dynamical gravity. But here the difference here is that in usual ADS-CFT, I guess the dimension of this boundary is fixed by what field theory we are considering. So when you fix the boundary field theory, that by that you mean the fixing the dimension and topology and the boundary metric, etc. Right? Likewise here, that amounts to fixing some seed state or initial state, the chi. Right? So chi plays a role of the boundary theory here. So by choosing chi with certain local structure that specify the dimension within this manifold and topology and the metric for this initial state. And then as we evolve this state through the gauge transformation. So gauge transformation kind of corresponds to the RG transformation in the usual ADS-CFT here. That's the picture. And then the radial evolution or RG evolution in this case in the ADS-CFT is now become some kind of time evolution along the gauge rule. Okay.
I guess I was maybe asking about the reverse direction. Like, so suppose, I mean, if this is a theory of quantum gravity, you should be able to, in particular, describe geometries that are asymptotically ADS. And then can you somehow see why they are equivalent to a CFT in one less dimension? Like, assuming that this is a good theory of quantum gravity, then maybe it should imply the conventional ADS-CFT correspondence, right? Or
you mean for the first case here, in this case?
Yeah, but where you describe the bulk using your theory of quantum gravity.
First of all, the bulk doesn't have to be ADS space. Okay, the bulk the space time is dynamical, and then depending on what boundary theory you are studying, you have a different bulk geometry. It may be, if you have a gapped system, the geometry is not ADS anymore. Okay?
It should be asymptotically ADS for the ADS correspondence, right?
Where that's the case if your UV theory is a CFT, but even that doesn't have to be the case in general. Your UV theory doesn't have to be CFT, right? I mean, mostly that is convenient to study. You can start a UV theory and add some deformation, and to study how the geometry evolves from ADS at UV to some different geometry in the IR. That you can do, but it is not. I think it's not always the case. You may have a UV theory that is far from CFT. Imagine you have a UV fixed point that doesn't have that is not a CFT, and then in that case, even asymptotically, the geometry is not going to be ADS. Of course, it'll be harder, but
Okay, but just let's, for simplicity, consider the case where you have a geometry that's asymptotically ADS.
Yes, okay.
I mean, so the geometry is dynamical, but there's some kind of classical limit where you can say that it's ADS, right?
Right.
And so then, is there any, so then somehow it should look like a CFT. But can you see that from your general quantum gravity theory?
So, yeah. So first of all, I guess you're referring to this current setup, right? In this setup. In this case, the bulk spacetime you get is not ADS in the first. You have a more like distal space. Okay.
Oh, but sorry, can it be ADS depending on the depending on the state?
Yeah, I mean, for some other state, maybe you can, but I don't know what kind of initial state will give you ADS.
I guess Dominic is just asking within Sung-Sik your general theory of quantum gravity, can you derive the usual ADS CFT?
Yeah, that's what I was asking.
Oh, not within this particular theory.
Yeah, within your theory, can you derive the usual ADS CFT?
Yeah, so that was what I was trying to describe here. So here, what we have to do is replace the initial state here, seed state, with a field theory action. Okay, and then replace the gauge transformation with a Hamiltonian constraint with the RG transformation. Okay, then one can see that the collective variable that you have that become dynamical inside the bulk include dynamical geometry, and then as we approach the UV, that has some fixed geometry in the UV. Yeah. So there's a general, I think, framework to do that. In a sense, that's easier actually, because there you don't actually you can do everything in Euclidean signature as well.
Sung-Sik, the short answer is no. There is no ADS CFT here, right? Is that right?
In this particular, in this particular model, no. But the framework that gives rise to ADS CFT is very similar. That's what I was trying to describe. That framework is to where you replace the initial state chi with a field theory action, right? And then Hamiltonian evolution with the RG evolution. Okay. So,
okay.
Yeah.
Maybe we should move on. Matt has a question. Before that, I don't know who should I ask first. Maybe Matt, go ahead. I have 2 questions posted on the chat as well. But Matt, Professor Matt Strausler, please.
A couple of quick ones. The first one is the parameter alpha. Is this a theory with a real parameter, or is that parameter just scale out and it's really either 0 or non-zero?
It's a real parameter, and depending on, there's some critical value of alpha that allows some non-trivial space of physical Hilbert space. So it's a real dimensionless parameter.
Do you have any more insight into what it means?
So basically, we want to have Hamiltonian to be 0 as a gauge constraint, and then we want to have non-trivial phase space that satisfy this constraint. And if alpha is too small, then it is impossible to satisfy this constraint. For example, if you choose alpha equals 0, right? Then the first operator is negative, definite. Well, except for very special state, very trivial state is negative. So you don't have non-trivial physical Hilbert space. But then as you crank up the alpha, you enlarge the space of physical Hilbert space that satisfy the gauge constraint. Okay, so roughly speaking, I think alpha tune the size of the physical Hilbert space very roughly.
So in particular, the algebra is fine for any non-zero value of alpha, but the Hilbert space doesn't function properly.
That's right. That's right.
Okay, so then this actually is related to my other question, which is in the solutions that you found, that you showed us.
Yeah.
How would those solutions have changed if you changed alpha?
I haven't studied that systematically. I have chosen a particular value of alpha. I forgot, maybe 1, where I know I have a non-trivial physical Hilbert space.
But it doesn't scale out of the classical equations either.
No. Yeah, it depends on alpha.
Okay.
I don't know the answer. How, if I change alpha within the region where there's you still have non-trivial physical Hilbert space, how the solution depends on alpha? I don't know the answer.
I mean, I wonder if it for some maybe for large. Well, I don't know if you could take alpha large, but I wonder if there's some way to simplify these solutions. I mean, the solution is for given the simplicity of what you started with, there in a sense, this solution isn't as simple as one might have expected. And it's very interesting, but I wonder if there's even simpler solutions hidden in here.
Yeah.
Okay, thank you.
Okay, then my question, people can still stay if they want. So I just want to make the comments on no global symmetry in quantum gravity first, and also the second about the Weinberg-Witten theorem. Is that a reason, maybe just because, should I suspect that you don't have a black hole yet in the quantum system in the setup you have, so the no-go theorem on this no global symmetry in quantum gravity does not apply? That's the first issue. And second one is that because there's no spin 2 graviton, or is there a dynamical spin 2 graviton in your model? Or is that because there's not such thing yet, so Weinberg-Witten theorem doesn't apply?
Yeah, so
just,
here,
just to no-go.
Yeah, I guess here the first space-time itself is emergent. So in that case, I don't think Weinberg-Witten theorem applies. And the spin 2 modes are present because this bilocal excitation can be decomposed into towers of local excitation with different spin, where spin basically corresponds to the angular momentum between these two relative, for the relative coordinate between two endpoints, right? So it basically, roughly speaking, this bilocal object can spin, and that angular momentum can be 1 or 2, etc. Right? So there are spin 2 modes. What I don't know is whether the small fluctuations of those spin 2 modes can be shown to be same as the spin 2 mode, the Laplace mode as in GR that I haven't succeeded yet, because I couldn't yet find a static space-time solution yet. Or the solution that I could find is this shrinking and expanding. So yeah. So but I expect that can be done, given that at long distance scale the constraint algebra coincide with the hypersurface deformation algebra of GR. But I don't know the answer yet. That's the thing that I want.
Yeah, another issue is no global symmetry. So the construction model introduced a large flavor symmetry. Should they be gauged, or should they stay global? And if that's still global,
yeah. So I don't know.
Or is that consistent with no global?
I don't know what are the. I don't know the assumption behind that statement. No global symmetry. I am not familiar with it.
I think the argument require if you have a black hole and you try to show charge states, and I think there will be lead to some inconsistency, even include discrete symmetry, or even I think even CPT or fermion parity. So fermion parity must be gauged if it's locally a symmetry, then it must be gauged and time reversal, etc. I think include everything. So not even mention the flavor symmetry.
So, but why are you saying that there's no black holes? Could there not be a state in this theory that corresponds to a black hole?
I don't know. Maybe this system has, but at least not the. We don't see in this talk yet. I don't know.
Yeah. Sorry, I don't know the answer here. Or I can say is this all the gauge generators are OM singlet, or OM being the flavor rotation. And you can consider different states with a different charge for that OM, or with a different broken symmetry. Is the maybe the locality of the maybe part of the assumption in that statement? I don't know.
So in your theory, how can I add matter?
Where matter and geometry are all within this collective variable. So as I mentioned, this T bilocal object includes spin 0 mode, spin 2 mode, etc. Right? Or higher spin mode as well. So that includes scalar field in particular. Okay, so in that sense, it describes both matter and geometry together.
I see.
Okay, if no more question, if you still have, you can still speak up. If not, I think we should thank Sung-Sik again first. Thank you, Sung-Sik.
Okay, thank you.
Good. And people can still stay.